unless you understand the toolbox is really clear, and there's no way you build bigger things without understanding basics very solidly. All right, so again, let's put basic neural nets into our nutshell. It can be used for classification, regression, and the majority of the state-of-the-art deep learning. So used to, people think deep learning is more about multi-layer perceptron. And now, I mean, the majority of the novelties in deep learning is actually in the representation module. There are just enormous variations. CNN, RNN, all the things I'm going to cover next time, they are just some variations of network topology or topological variations of how do you represent the data. And the majority of the scoring function, and mostly we use negative log likelihood. And we actually covered negative log likelihood in the logistic regression session. And in fact, that's just, in the end, you're modeling the output variables in the logistic or in the binary classification case using a Bernoulli variable. And when you're modeling the output variable as a Bernoulli variable, and the likelihood, maximal likelihood estimation, it's exactly equivalent to minimize the negative log likelihood. And it's also extended to all multi-class case, which I'm going to cover in detail today. So how do that even related to maximal likelihood estimation to the cross entropy loss in the multi-class case, which is a bigger detail I'm going to cover today. So in terms of binary classification, I want to add one more discussion here is, so for the binary classification, how many different loss functions we have learned so far? Just a question. How many different loss functions we have learned? So for the regression, we always use sum of squared area. For the binary classification, because the most straightforward is to minimize the number of misclassifications. However, you can differentiate that loss function, so that's why people use various different methods, use different proxy of that wrong misclassification. We have learned 2 so far. So what is that 2 we have learned? The 2 different loss functions we have learned. The first is, so the first one we learned is in the SVM case. So what is the loss function in the SVM? Hinge loss, yes. And then the second we learned is in logistic regression, which is actually maximal likelihood. But because in this kind of formulation, you normally see loss, right? So you maximize likelihood, you minimize the negative log likelihood. Yeah, so there are 2 different loss functions we learned. Hinge loss, we learned in the SVM case. In the logistic regression, it's called negative log likelihood. Which essentially is MLE, a maximum data likelihood, equivalent to minimize the negative log likelihood. And it's because its formulation takes the form like y choose times log if you remember the logistic regression is Py equals to 1, conditional x equal xi, and this we normally write it as, because this is a probability, right? So you are actually trying to predict 0, 1, but you're using that probability as the predicted yi. So we normally treat this as the yi hat. So this formulation, so if you ever learned about entropy, we're going to learn the more details about what is entropy. The definition of entropy actually, in fact, is yi log yi. And so that's why this is actually called cross entropy. So in the entropy case, if you ever learned about entropy, is the P log P is the entropy. We're going to review that, and that's the definition. And this is just log P, so the probability, right? And here is not that P, but in fact, it's the true observed yi. So that's why we call this cross entropy. So there are two vectors, true y vector and the predicted y, which are the probability, and it's a variation of entropy definition. So that's why this is also called cross entropy laws. So there's a reason behind why this is called cross entropy laws. Yeah, so and the multi-class case is just exactly an extension of this Bernoulli variable into a discrete variable with more than two class, so which I'm going to cover in details. All right, so hopefully you remember this, and the basic is the single neuron, and then when you have many neurons, like kind of composed in one layer and then composed with multiple layers, that's multi-layer perceptron. There are all these different variation of loss functions, and you train this into neural nets through a back propagation. Jack did a really concrete back propagation step-by-step derivation last time. So again, so just to recap, we really just rewrite logistic regression through two stages, right? The first stage is Z. Z is a linear summation of x, and then we perform this function called sigmoid function. I hope you still remember. The sigmoid function has this EZ over 1 plus EZ format. So, and it's essentially just decompose logistic regression into two stages. Summation stage, which is the Z, and the sigmoid stage, which is the squaring function. It's represented from Z to Y in the logistic regression case. So, and we call this single neuron. So there are a lot of variation of this type of summation then plus a squashing function. And other than just the sigmoid, there are many different kinds. And Jack covered the first kind is called a step function. And then there's also like logistic function. There are many 10H function, rectifier function. There are variation of rectifier functions, many. So currently, the rectifier function is used a lot, and previously the 10H function was used a lot. And the reason, in the end, it's when you think about all those scoring functions, very important is if its gradient is easily estimated or not. And the step function is just the gradient, like Jack pointed out. I mean, you don't even have gradient because the step operation. So, however, in fact, why multilayer perceptron is called perceptron? It's because the reason is perceptron is that type of neuron with the summation function plus a step function. In the history, when it's first invented, is only the step function. And this combination is called a perceptron, and that's the reason why we call everything later of the composition of this type of summation and plus a nonlinear squashing function is called multi-layer perceptron. And this is the first type of neuron. It was when it was invented, so that's why it's called perceptron. So just a little bit of history to let you why it's even called perceptron. It's because in the beginning, that stacking function. Okay, so you talk about this, and then you normally treat a summation function and a sigmoid squashing function together as one neuron. And then there's a question that I think I want to emphasize is, so we normally have a bias terms here. So it's kind of, why do I need a bias term, right? So it's actually about what you can represent without or with the bias term. If you don't have a bias term, after the sigmoid function, so let's just think about this, after the sigmoid function, it can only represent the variation is only just about how squashing it really is, how steep I'm pushing my squashing to be really like a stepping function or like a smooth stepping S function. So how steep is that S shape? And it's always passing this 0.5 point, of course, right? There's no bias term. Whatever x1, x is 0, it doesn't matter what weight it really is, right? It always pushes to 0.5. But with the bias term, you actually can represent 1 is the S. I mean, when do we push to the 0.5? Or, so the bias term is actually necessary. So I hope you understand. So it can even push into the 0 very, very early, or it push to the 0 very, very late. So there's a bigger proportion in the blue line as the 1, but there's a smaller proportion in the red curve as the 1. So can show that kind of cost or balance among the two. So if without the balance term, without the bias term, it's always like a balanced half-half. Okay, so this is the first I want to emphasize the details. And then we talk about, you just treat each one of this as summation and squashing function, and that's one neuron. Then you can have multiple neurons in one layer. All the input can just feed into every neuron, in the same layer, and you generated the first layer output, and then feed together into the second layer. So together, every weight here is, we normally call that matrix W1. All the param here is the second layer, it's actually a matrix W2. And then last layer, and then this problem, because binary classification, we have only one output, and then we use the sigmoid to project it into probability space. So this is the binary classification or regression. All right, so what does this composition multiple neuron even does geometrically? Okay, so let's first see what do we even have for the logistic regression geometrically. So this is the sigmoid function. So this is the sigmoid function. We have x to summation layer, and then that's the output z. Then from the z, we have a sigmoid function go to the y. And this is our fx. So this actually represents the z, and this represents fx. So, the z layer is the output of summation. It can be positive infinity or negative infinity, like we try to explain in the logistic regression case. The first phase is just a summation. It can be anything. And then you squash it through that sigmoid function to compress all the values into 0 to 1. So that's the function of sigmoid, right? If looking at from the output surface, this is actually this is a contour map. So I'm coloring, the more negative, the more blue. The more negative, the more red. The more positive, the more blue. And you can use this heat map to show what's the output space looks like, right? Because I already emphasized to you, logistic regression is a linear classifier, which means the the point on here, so the point on the 0, this is my boundary points, right? I should not use curves, but just to let you know. So these are my decision boundary, right? So if without the squashing function, so this is the z space. The left is the visualization of z. The right is the visualization of alpha y hat or fx, the final y. So it's the fx y hat. So it has that kind of properties. It's kind of squash a lot of things close to 0.9 to 1. It's reflected in this one too. It depends on, of course, the stiffness, but the majority, so no matter what is your z, so this is the x-axis z, it's showing z to y. So this is the z, and this is the output fx, and z is equivalent to double transpose x. I hope you still remember. And this is the summation. It can be positive to negative. And this is the fx, is the probability. You can tell everything here, there's infinite number of values, all pushed, majority of value, they all pushed to be very, very close in the output space. And that's exactly represented by this figure. So in the end, just the 0.8. So here it's more it's very subtle. Here the probability changes very subtle, and the more there, the probability change very slow. So it's more that's the positive. You can think about there's a step function, but the smooth step function like we covered in the SVM. So what is classification really learn? So this is actually the X space, right? So the color shows the fx. Here, color shows the z. But it's all X, and this is surface map. You can think about surface map, using this color to show the intensity of the surface. So there's a huge amount, go to that side, it's all very, very slowly from 0.8 to 0.9 to 1, 0.99. And there's a lot of subtlety here, and there's almost no subtle changes on the y space. The more you're far away, the more you're far away from the decision boundary. So this is just to show you what is one neuron trying to learn. All right, so now let's see. You have first neuron, so let's just use an example, and it's trying to learn this kind of decision boundary. And this is the second neuron, it's trying to learn other kind of decision boundary. So when you put them together, so when you have two neurons together, what you're learning is not the two anymore. It's a soft combination of this and this. And so you can tell, so because of this, majority got pushed to 0 point. So I think red color means positive. Blue color means negative. Yes. So this is the positive, and this is the negative. And this is the positive, this is the negative. And the combination on each point, it really depends on the weights of this combination, right? That's actually, this is the second layer, W2, and this is the first layer, W1. And together, and for this part, it's actually very easy to tell, right? It's just the weighted summation. No matter what you are, it's always will be negative if the weights are not in the same, their same signs. So assuming the weights here are the same sign, so the negative here will also be, because this is also negative, and it's the same same sign on weights. So of course, this part will be negative. And also this part, and also this part will be positive. But this part, because it depends on what contributes more, it's kind of, it depends what contributes more. It's this dominating or it's this dominating. And that's why you got this kind of shape. So I think in this problem, this is not dominating over that. So that's the reason why this part is still positive. And this is not dominating over that too. So this part is positive. So in the end, it's really just combining two decision boundaries and then into a soft piecewise function. You can think about this as more like a soft piecewise combination. Of course, it depends on the weights, right? It depends on the weights. So this trying to show what do two neurons really do. When there's one neuron, split the space into this. There's another neuron split into that. And then the combination depends on the weights. And it's a nonlinear, you can think about almost a soft, piecewise linear decomposition of the space. All right, so this is trying to show what do composition multilayer even mean. So what? Sure.
Can you overfit the data?
Of course, you can overfit the data.
If you have a lot of neurons.
Yes.
And
so here I only show you two, right? Only the two is a piecewise shape, and when you have more, I mean it's a lot of decomposition and very complicated. It also depends on the weights. Depends that on the second layer of weights.
And in that case, you have to remove some neurons when it's overfitting.
So how do you know overfit, right? So this, in the end, it's a bias versus variance trade-off issue. It's how complicated your task is. How complicated, it's in the end, it's how complex is your it's your target task really is. It's not about 4 layers, it's more easy to vary, or 3 layers more easy to vary. It's actually about the task. Yeah. All right, so question about this is just trying to show visually what do I mean 2 neurons together and do a second level composition. It's a very easy virial composition. Yeah. All right. So yeah. Also, you understand why I'm dominating, right? Because there are very fewer. It's not very. So this is not very sure, because this one is not very sure. And yeah, it's actually because this part is not very sure for this classifier. So that's why this is dominating. And because it's so close to the boundary, all this are related to the squashing function, and also, of course, depend on the weights on the second layer, 7 and 5. All right, so now let's talk about scoring function. So the majority of scoring function for regression case, and we always use sum of squared error. So now I'm expanding the regression we learned before into multiple different regression. So what we learned before, there's only one output variable y. But in the neural network type of formulation, it's actually extremely easy to have multiple y. And in this case, I have 2 different y output variables. How do you consider the error? You just do summation of the first output variable, the square root, the quadratic differences plus the second quadratic differences, and extremely easy to calculate its gradient. It's just 2 over and then versus that y. I mean, so yeah, so it's extremely simple. Sum of squared error for regression, and I think Jack covered. We actually covered binary classification cross entropy loss, which is exactly this formulation. And the reason is we are assuming we have our output variable is Bernoulli distributed. So I hope you still remember what is Bernoulli distribution. It's a flip a coin, head or tail, right? There are only two possibilities, and there's only one parameter for a Bernoulli distribution, which is the p head. For Bernoulli distribution, and the Bernoulli distribution is drawing the py given x is, it doesn't matter what y, it's this formulation. I hope you still remember. Yeah. So py given x is a shared formulation of two cases. It's p head, if it's a head, and 1 minus p if it's a tail. So, yeah. So, and the loss function is just negative log data likelihood, and this is data likelihood. All right, so again, so while you're doing logistic regression, what you observe is y1, y2 onto yn. This is your training data, right? The data likelihood is p because in your case, it's not just y, but there's also x. We just represent y conditional x as z. And this z is a Bernoulli variable conditional x. So this is my data likelihood, and it's equivalent to py conditional x over data. So then your likelihood, just because this is a Bernoulli variable, you just use whatever you did for the Bernoulli data likelihood, and you just substitute the p with that parameterized by the x. So this is a recap. And so it just one thing need to kind of clear is, yeah, maybe this page. So in the Bernoulli case, we are assuming the target variable is a Bernoulli variable. Its probability parameter, that p, is not a scalar, but it's a function. That probability head is a function related to the data input x. And it's in fact is the sigmoid function ez over 1 plus ez, right? So so this is for Bernoulli case, for binary classification. But when we formulate multi-class classification, it's very, very similar. In the binary case, we use Bernoulli. In the multi-class case, for example, you roll the dice. I mean, it can be 1, 2, 1, 2, 6, and then it's a discrete probability, and this is essentially it's a multi-Norley distribution, and the parameters is py equals to 1, py equals to 2, py in this formulation. And in that, if p equal to 6, we have only 6 possibilities. For this type of discrete probability, to represent its probability distribution, you need the 1 possibility, 2 possibility, 3 possibility onto 6, in this case k. There are k parameters you need to estimate to get this probability formulation. All right, so how do you do this in the neural nets case? So, in fact, because I'm writing this as 1, 2, 3, 4, 6, but in fact, there's no numerical relationship 2 is larger than 1, 6 is larger than 3, or 6 is larger than 1. at all, right? It's really just the first phase. First phase, second phase, third phase, they have no relationship at all. So you can use the numerical value as 1, 2, 3, 4, 2, 6. There has to be a way to represent a discrete representation, which is exactly your homework 3. You use categorical basis vector representation to represent each possible outcome. If the basis encoding, basis vector encoding, for example, if this is class 3, and if there's total k possibilities, then you have k output variable. Just y1 until yk. You have multiple output variables. However, if it's the class 3, you label that class 3 as 1. If that's class 2, you label that class 2 as 1, all the other as 0. So now I'm converting one single variable output into actually 4 or k random variables. How do you represent it? So in the end, the rule of thumb is I'm converting my problem into k different regression tasks. For each regression task, there is fkx output. And I'm assuming this fkx output is a probability, follows the probability, is the pkx. So you have p1 until pk, and the summation is 1, then it's exactly what we learned. The base classifier is the classifier to use here. We do argmax on this k different regression output, but that regression output needs to be converted into probability to satisfy the base rule requirements. So this is what we covered: discriminative classifier, and the most important is to be able to model that conditional probability p, y, y1 until yk given x, and use the argmax. Whoever give me the argmax, it's my prediction. So, and this converted a multi-class problem into k regression task, and then you do argmax onto this k regression. So, and how do you implement this? And this is exactly something called softmax layer. So, because the multi-class output, I converted when there are k possibilities, I converted into k regression task, which is represented from whatever regression task, there's output because it's z1 until z3, because I want to guarantee the true compared, its probability, right? I have to convert the z1, z2 until z3, that 3 different regression tasks, their output into a probability formulation. And how do you convert it? This is a classic softmax function. It's e zi over summation of e power of zi. And this can guarantee the fx, f1x plus f2x until fkx equals to 1. And also each one of them is bounded from 0 to 1. So this softmax function can guarantee the output looks like a probability for Martinoli distribution. Question about this? So again, for single output binary classification, you don't need to have 2 regression, you only need to have 1 regression task, then converted that regression output from -infinity to +infinity into the probability p hat, right? However, when you have multiple class output, you need to convert it into k regression tasks and then smash the k regression task, that regression output as a probability, and then use the base rule to get best prediction, and which actually is almost the best prediction based on the base rule. This is a one kind of discriminated Bayes classifier. All right, so so it's in the end it's a discriminative multi-class output, but you implement it through k different regression, and then the regression output is z1, z3, and then you use this softmax function to convert it into probability, which is equivalent to we're modeling the output discrete random variable using a Martinelli random variable distribution. And there's also a good thing of this, the softmax function is the gradient of the softmax function is extremely easy to write. So y versus the z, and this is its gradient equivalent to yi times 1 minus yi. So I'm not sure if Jack did really careful derivation about why do I care about this, but let me show in the next page. Okay, so you have k different regression, and then you put them together. This is geometrically equivalent to what? Assuming there are three cases, it's geometrically equivalent to I'm separating the space into three regions. If there's only one layer, so assuming not multiple layers, only one layer of summation, it's equivalent to I'm using linear boundaries to separate each pairwise class. So if there's only one summation layer from x to the z, and then it's called Martinelli multi-class logistic regression. Multi-class logistic regression multi-class logistic regression, you can actually do the proof, which I did before. So what do I mean decision boundaries? This decision boundary means this class is zero, this is the probability of belongs to this class equivalent to the probability belongs to this class. You can actually derive, and this is a line. This follows a linear form. And every pairwise follows a linear form. It's equivalent to I'm segmenting the space into k regions using linear separation lines. But that's just one layer. And the reason why I'm talking about this is think about this page. So this is for binary output, right? And if you use sigmoid, it's like this. However, for the last layer, if what you care is multi-class output classification, this type of sigmoid Gaussian function cannot represent multiple classes. And the sigmoid and the softmax has the ability to segment your space into multiple different classes. So normally not sigmoid, softmax. Softmax for multi-class classification is used the layer before the last layer, and because it's a Martinelli distribution, similar to the Bernoulli, you're doing MLE maximization. It's MLE, maximal likelihood, data likelihood, equivalent to minimize the negative log likelihood. Negative log likelihood, and it's also has the same form called cross entropy. And the only differences here is in the logistic regression case, you have y hat log y hat predicted plus the 1 minus y hat and then log y hat. But now, because you have all the k cases as the parameter, you only just have the same form and summation over all the possible k cases. So in the logistic regression case, what you have is y log y plus 1 minus y log 1 minus y. So that's the logistic regression case, binary case. So in the binary case, you have this form. In this multiple case, you have this form. In fact, that's the same form. It's just in this form, this is more generic. You can represent k different classes. Here, you're using only one regression, and the other regression, the p tail, you don't need to represent it because when you know the p hat, the p tail is already defined. It's 1 minus y. You don't even need to calculate it. So I think that's the next page, this page. So in fact, the logistic regression is just a special case of multi-class classification using one regression to implement. And if you use this multi-class case, you have E, the first output versus the head output or the tail output. You have two cases, head and tail. And for head, you have a parameter, z head. You have a tail, you have a parameter e, z tail. In here, I represented 1, 0, right? Head and tail. And in fact, it's equivalent to 1 over 1 plus e minus z1 minus z2. So logistic, it's really a special case that avoids use redundant parameters. So let's just summarize. The cross entropy has this formulation, and I just want to emphasize this is the true y and log yi prediction, and then it's equivalent to summation over all the possible cases, j from 1 to k. And then the whole point is the multi-class case is just its parameter, it's each p, p1, p2, until pk. Each one of the parameter of that multinull distribution, that parameter is a function conditional on x. And also this cross entropy loss, it's extremely easy to calculate its gradient. So when you have cross entropy loss, its gradient has the form y prediction minus the true y. So, and this is actually exactly why back propagation is saying forward, I'm forwarding the signals until the end. Backward, I'm backing the loss from the output to the input. So the reason is, in the end, I'm actually backward the gradient. It just accidentally, actually not accidentally, the gradient has the form is this type of form, which is the error. The error you're making on the ice data is the yi minus true yi is the gradient of that loss function. And when you have the cross entropy loss, my gradient is directly yi minus true yi. When you have SSE loss, so let's just see, if your loss function is, assuming, is the SSE loss, y minus y hat taken quadratic, this is another loss, right? So what it is its gradient function? It's actually 2 y minus y hat. So this is the first case, this is the second case. The oldest error function we use, its gradient all has this form is the error from the true prediction minus the predicted prediction. And that's why we're saying the backward propagation, we're propagating the error from the last layer to the input layer. And because we are back propagating the gradient, there's nothing special about this at all. It's just the gradient has the form is the error. All right, so now it's block view of multi-class. It's really just, so everything before is the same, and the squashing function only in the last layer before the error. Last layer you replace it into softmax function, and this makes you to be feasible to do multi-class classification. And I think in the end, you're just treating each one of them as a block. And the summation block, squashing block, then error function block. And there are some blocks you have parameter to learn. There are some blocks you don't have parameter to learn. So, and then you just use the stochastic gradient descent. There's nothing special of the deep neural nets optimization at all. It's just stochastic gradient descent. Nothing special. It's actually what we learned, theta t plus 1 equals to theta t minus the alpha of my the j function of that times the error function over theta. In our case, the same thing. The error over w, it's just our w is extremely complicated, right? It has this layer-wise structure, these the first layer, second layer, until maybe the t's layer. That's the whole thing of what I need to estimate. It's extremely actually just very modular. And that's why people, and because it's a modularity, I actually can separate the gradient of this from the gradient of all the previous layers. When I have this is the last layer before the error layer is only related to the error layer. So so yeah, this is all covered. I mean, so it's in the end, for all the layers, you're starting from the output layer back to the input layer. You compare the network output with the correct output. You adapt the weights in the current layer with the layer propagated from the layer after. And so you can have a lot of variation, mini batch version. The mini batch version of SGD is the major uses in deep neural nets. We don't normally do single point stochastic gradient descent. We normally do a batch of the points. You sample a batch of data, you forward propagate it through the network to get a loss, then you back propagate to calculate the gradient, you update the parameter using the gradient. So I hope you're got a really good understanding how to calculate this. And what we mean forward is, so what do I mean forward? Let me do a check of Jack's teaching. What do I mean forward in here? In the green arrow, what is the forward for this module? Forward.
It's the input propagating to y.
Yeah, so how to get y? It's a very dumb question.
Yeah.
What do I mean forward? Yes, fx. That's forward. Okay. And then backward, actually I already had it there. What do I mean backward here? Backward means I got a gradient from the layer all after me. This is because, so what do I mean gradient? Everything is about that error function, right? Stochastic gradient descent. Everything is about that final loss function versus the parameter. So everything here is that loss function versus the layer after me, and I got this gradient, and then I'm propagating to backward. So what do I mean I'm backward propagating is the gradient that I get from the layer after me times the gradient from my current layer. So what is the gradient of my current layer? The gradient of my current layer is y over x. That's my local gradient. What I'm propagating backward to the layer before me is, again, is the loss function for the x equivalent to the log function versus y times the y versus the x. So who has question about this formulation? This is the most basic chain rule of calculus, right? When you have a function can be decomposed into the everything about y and y about x, and it's really just so this is because e is f. Let me if I write as f. Yes, e is some kind of function f maybe y, and then equivalent to f and g x. Actually, no, that's not good. Let me write here is gy. Yes, yeah, this is good. So assuming I'm just summarizing everything after y into a g function, everything after this is a g function, gy, and then give me the error, the loss. And then e equals to gy because y equals to fx, right? And e equals to g and f. So that's the reason why if I'm calculating gradient of e versus the x, it's equivalent to what? It's equivalent to I'm calculating e versus the g in this case actually is the y and then y over the x. Okay, so I hope this is clear, very, very clear, because of this composition of functions. Okay, so and then you propagate this to the previous layers, and this is you get from the layer after me. So let's use an example. So assuming this is my sigmoid layer, sigmoid neuron, what I get is everything from the output of that sigmoid function. I can treat it as z, let me treat it as a y. So it's equivalent to, I'm just treating the function there, but it's the same as treating that output. And in the forward, I'm forwarding the output fx, which in this case is sigma x. In the backward, I'm backwarding e versus this output y. At the same time, times this output y versus the x, which is the sigma times 1 minus sigma, which is equivalent to all right. So I think Jack did a very detailed derivation of this, right? Very detailed. How do you calculate, maybe, for example, error versus maybe W4, W5? So let me use an example to just to check. Is it easy to derive? Maybe W5. What is, because when I'm trying to updating W5, what do I need? When I'm doing W5 updates, the specific W5, what do I need? W5 at teeth equivalent to W5 at T minus iteration minus alpha, the error versus W5. Okay, let me miss delta or maybe lambda. Yeah, maybe lambda it's easier to distinguish. Lambda is my learning rate. So which means to update W5, I only need error versus W5, right? Okay, so how to calculate error versus W5 in this case? So you don't even need to understand anything. Let me just do the simplest. Forget about everything about backpropagation. Let's just do the simplest calculation. E versus the W5, I should do E versus the Y prediction, right? First. Because that's my first output. And then from the Y output prediction versus the, this is really easy. Yes, W5. Okay, so what is it? E versus the Y hat is what? What is its gradient looks like? 2 Y minus Y hat. Minus, yes, there's a minus before. And then Y hat versus W5 is what? Actually, I don't need to because it's H1, right? Let's see, Y hat is here, right? This is the equation of Y hat. Y hat, the whole Y hat, if taking gradient versus the W5 is what? H1. Okay, so this is so easy, right? But it actually already represents what? So this is that specific output versus my W5, and then this is what? This is what propagated from the loss layer to me. I only care about summation, and then the loss layer to me is this phi E, phi Y, and then times myself. And because I stop at that summation function. Okay, so now let's look at a more complicated case. E versus W1. So how do I calculate this? Sorry, that is a little complicated. So how do I calculate E versus the W1? Because I need the W1 if I want to do the W1 update. T equals W1, T minus 1, minus the lambda, phi E, gradient versus the E versus the W1, right? So that's the only thing I need to do the stochastic gradient descent. And then how do I calculate this? E versus the W1. So I have to do, because this is like F4, F3, F2, F1, right? And the W1 is related to the F1, if we look at this. And I have to go straight backward to the F1, and then versus the W1. And it's equivalent to F4 over F3, F3 over F2, F2 over F1, then F1 over W, right? This has nothing related to the backward propagation at all. It's really just functional chain rule. So let's see what is the last term, F1 over W1. I hope you can read. I'm sorry, it's pretty small. It's X1, right? Yes. And then what is F2 over F1? So this is actually pretty complicated, right? I mean, let's actually just look at the block view we had. So each one of them here is a block. And for every block, what I care about is input. It's in, it's out. In X, out Y, and also its gradient versus its in. Out versus in for every block. So let's just see what is it. So for the first module, let's just use A example. Its input X is, in this case, actually is X1, X2, right? And also W1 onto W4. Its output module is what? It's Z1, Z2. And its input output, you can do the calculation, depends on what you care. So for example, the Z1 over W1 is X1. You can do all those kinds of formulation. In the second module, F2, its in is Z1, Z2. Its output is H1, H2. Sorry, I have it already. So to save time, so for every module, you write out its in, write out its out. And then you can calculate every combination of its out versus its in. And then let's see this calculation. So E versus W1, in the end, you can write it as the minus 2y minus y hat, W5, H1 minus times 1 minus H1 and X1. And this is exactly, so this is F1, F4, the F4's in versus out. Is this one? So this is the first modules, F4 modules gradient. So the first term is F4 modules local gradient. The second term is F3 modules local gradient. And this is F2 modules local gradient. And the last one is itself, related to itself. You can see the error versus the W equivalent to what? Equivalent to error modules gradient. Is equivalent to the error modules gradient, this first summation modules gradient, and then that sigmoid function gradient, and then the last gradient is the summation related to it. This is exactly, so this calculation is exactly F4 to F2 to F4 to F3 to F2 to F1, which is about this. So let's see the error back propagate from the error module, then back propagate to the F3 module, give you H, then back propagate to the F2 module, give you Z, and then at the last layer, it give you the local gradient that's necessary for the F1. It's really this calculation. You can see every is propagate from error to the one before, the one before, until right to the module related to me. So this is, in fact, the whole back propagation is really just chain rule, but it's just more, it's just a new terminology of the chain rule, considering the layer-wise structure, and also because of the block structure, it's kind of isolated. To calculate the parameter related to, for example, to calculate the parameter related to this layer, I do not need to do anything related to layer before me. If that's the input, this is the output. What I only need is all the layers more close to me to the error layer, and that's about it. There's nothing more. So there's some tricks about how do you look at the loss curves. So you really need to be careful about if there's super high learning curve, Low learning curve, it might convert this really, really slow. The really high learning curve, it might convert this to a bad solution, which gives you really high loss. So learning curve is a very tricky parameter in deep neural nets. A good learning curve is hopefully give you good, smoothly degrading loss functions. So that's very, very tricky. That's the first thing tricky, and the second tricky is, so you need to look at the training loss and versus the validation loss. Are there big gaps? This one uses accuracy, so which is the reverse. So how do you know you're overfitting? How do you know you're underfitting? So this is really related to the homework 2 we did. And then there are a lot of tricks in deep neural nets about the magnitude of the gradient because you have so many layers. So let's look at this. Because you're calculating layer times layer times layer. If your layer is really, really deep, there are so many multiplications, right? And this will create numerical instability. So that's why there's so many tricks. There's many tricks in deep neural nets. How to guarantee the magnitude of the gradient is not too big, it's not too small. So there are many tricks. So I'm not going to cover that. So there's this archive paper. It's a very great summary about how to control all the tricks. Momentum, atom, graph, all this. There's so many of those. Okay, so I'm very slow today. Okay, so yeah, let's talk about the next time. Yeah.